Kadena, what are we talking about today? We are talking about what is Kadena, and specifically I'm going to talk about Chainweb, which is our public network. We have a public network, a private, and a smart contract language, which if you were in this room about an hour and a half ago, you heard Joel talk about Pact. And Pact runs on both our public network and our private network. So we can run pretty much anything that you need in order to develop a project on a blockchain. So what is a blockchain? You've heard variants on this from several people today, but it's a distributed ledger. Information is replicated without somebody in the middle making sure that everybody all comes to consensus. So how is consensus decided? It's with one of these protocol mechanisms by which, like, for example, old school Byzantine fault tolerance, where everybody votes and then the votes decide who comes next in consensus. So we have our own consensus mechanism based on Nakamoto consensus Bitcoin, and we'll go into that in this talk. So what is a blockchain? Can record timestamps, currency transactions, code to be executed, and more. Private blockchains, we have a private blockchain. You have to be allowed to participate in the network. So imagine like Goldman Sachs and JP Morgan and Morgan Stanley each have a node and they all talk to each other. Private blockchain. We have an enterprise blockchain and we already have people using it for other projects with Pact on top. And we also are developing a public blockchain with Pact on top. And this is anybody could join and spin up a node and mine blocks on our project. Okay, so start a little diagram. So the toolkit for Pact and the development language are done, functional, and constantly evolving. We are releasing Pact 2.4. I think it just came out like today. And it has a formal verification system that Joel talked about. And then you can use it either for public or for enterprise. So why are we here at LambdaConf? Because we love Haskell. Everything that Kadena does is written in Haskell. Pact is a Lisp and it's written in Haskell. And our blockchain is written in Haskell. There have been several blockchain projects here talking about functional programming and why it's so good for blockchain. If you wanted to know more about that, you should have gone to this guy's talk this morning. But basically, unlike a bug in a web app, where it means that you might not be able to like buy your shoes on time, a downtime bug on a blockchain is a big deal. And lost data on a blockchain means lost money. In this case, code literally is money on a public blockchain where you have a cryptocurrency. So humans make mistakes, but built-in type checking doesn't. And having purity in your functions to make sure that they access what you expect them to access is a great way to ensure that you don't screw things up. My team is making faces in the back, but they had a chance to read these slides and probably didn't, so.
Just type like a statement, type checkers don't make. Maybe different by different.
All right, okay. So other things we have written in Haskell in our project, aside from Chainweb, which the rest of this presentation is about, but I thought I would briefly touch on this. Scalable BFT private blockchain is written in Haskell, and it's one of these BFT variants. It's a raft, it's a variant on Tangaroa, it is semi-permissioned. Pact, Joel already talked about it, so we can probably just skip it, but it has lots of cool stuff. Okay, Chainweb. What is Chainweb? We use it for our public consensus mechanism. So the three features of Chainweb that I'm going to highlight in order to describe how it works: scalability, security, and speed. So scalability is the reason why people don't just use Bitcoin. Right? You can't pump a lot of transactions through it. If you could, then maybe we wouldn't need all of these other blockchain projects. So security, unlike a potentially questionable staking variant that requires game theory and slashing and hoping that everybody's a rational actor, proof of work works because physics works. And we have a braided proofing structure, which means that you get many hash link references very quickly, and we'll go into that as to why that's useful for proof of work and security. And then because we have this proving structure, we can have much quicker confirmation times. You don't have to wait for as many confirmation blocks for a transaction to be processed. So then we can have unusually high speed. Okay. So, like I said before, Bitcoin uses proof of work for consensus, Nakamoto consensus. We use it too. For traditional Bitcoin, your miners assemble transactions into blocks. Your block is some sort of fixed size. Once you pack enough transactions into a block, you race to solve the block using brute force, trying to make the hash match what you want it to match. Solutions are found, they broadcast everybody else, and then everybody piles on and keeps moving forward. So this is your Bitcoin style blockchain. So I'm going to try the laser pointer. Yes. Okay. This is one chain. You have at the beginning this one block, the black block. After the black block is completed, there's a reference in this red one which contains information about the black one, which is how you trace the blockchain. It's chaining the blocks together. Right. So the red one references the black one. The blue one references the red one. As you go forward, generating block height this way, the references point backward in time. So in this case, for the single chain, you have one header reference. So imagine that instead of having just a single chain, you could have multiple chains that use this similar proofing structure. Question?
At the bottom of that previous slide, what were those graphs?
What?
Just the bottom, the block height.
Oh,
graph.
here, block height. 0 block height, 1 block height, 2 block height, 3 block height.
Yeah, I was just wondering what the long black and red lines were.
Oh, it's this will become a three-dimensional graph later, and then it will become confusing to look at if you don't have those lines. They are marking block height over time right now. So this is 0, this is 1, this is 2, this is 3. That's the only reason it's three-dimensional, because it looks weird now, but it'll make more sense later, I hope. Okay. So we have many proof-of-work chains. They are braided together. That's the term that we're using to describe that they are connected in a fixed structure. So at launch, there's a graph structure. It doesn't change. The number of chains does not change. So it's not like, I spin up a chain for myself, and then that's not one of these. It's not a sidechain project. Then the chains propagate independently. I mine this one and I mine this one at the same time, and I find a solution grade. It doesn't stop me from working on the other one. And then they pass proof to each other, which keeps the whole network synchronized. The braid structure is fixed, but if we get clogged, then we can hard fork to a larger configuration. And having all of these chains means that you can pump through many more transactions than you would on a single chain. So this is our graph now. Imagine that instead of having one chain, you have two. And you're creating this block, the black one. And after you finish it, you start working on the red one. And the red one has a reference to it, but also you've made this block. This block, now you're working on the red one. The red one contains a reference to this guy, and this one contains a reference to this guy. After you successfully created your block, you broadcast it out on the message queue. Whoever's listening and knows that they have to contain the reference from chain one, listens to the message queue, grabs that proof, and shoves it into their next attempt. Questions?
Does each chain have its own supply, or is there one global supply of, let's say,
There is one global supply, and they are fungible between chains, and we will talk about the fungibility mechanism.
That's basically it. Answers my question. Could blue on the bottom ever not see the red at the top and thus point it black next to it?
No, it cannot, because you know what block height you belong to. Yes, okay. So,
why they point to each other?
They point to each other because they're fixed, and because the graph structure is fixed that way, and it gives you a security requirement, and also it allows you to pass information throughout the network. And we'll talk about propagating information and security.
Wait, so does block get updated when red's created, or is that because red doesn't exist, right?
Right, so these two black chains, these black blocks get mined independently. They're just doing their thing. When each of them gets made, they each broadcast out on their message networks. The black one's like, okay, I'm done over here on chain 2, and whoever's mining on chain 1 hears that there's been a solution on chain 2, grabs the proof and sticks it into their next attempt for the red block on chain 1.
Red has to wait for both red.
Yes.
possible for like the bottom chain to be like 3 or 4 blocks ahead of the top chain? It has to
No.
be no.
You have to wait.
Okay.
But if you're not linked directly to someone, then you don't have to wait for them. Which in this 2-chain structure, it's a little wonky because they're always directly connected because there are only 2 of them. But as the graph size gets bigger, you're only ever connected to degree number of other chains, and you can be as far as diameter number of hops away.
Okay.
So you only have to wait for your immediate degree number of peers. Yes.
Do network partitions cause the thing to fault?
So that's an interesting question. So the way that we're working on it now is imagining it like one giant Bitcoin. So that in this case, we will, if there's a wall between China and the rest of the world and they are mining their own Chainweb, then if the wall ever comes down, there will be 2 of them and then they'll have to decide who wins. Lars has some thoughts on how we might be able to save the number of lost blocks in that scenario, but maybe we should save that for another time.
But yeah, so for my change, the problems are the same as with Bitcoin, because the graph structure is not the communication structure. So the communication in the sense of the network communication. So every node has its peers, but any single node might mine any number of on any number of chains.
Yeah. In fact, we assume that everyone will mine all of them.
So the connection graph of the chains is completely orthogonal or independent of the actual communication that goes. So you might mine 2 blockchains, I might mine 2 blockchains, and we might communicate via someone else. But yeah, those are 2 different things. So the network partition does not go along the edges of this graph.
In Bitcoin, when a node receives a new block, it has to look at all the transactions in that block and decide if they are legal transactions in that context. Say they don't spend an output that's already spent, they don't spend an output that isn't in the preceding chain.
Right.
In these blocks which merge in a reference to another chain, how does the node decide whether the block is permissible?
So in this case, this goes back to his question about fungibility, whether it's one global supply or a particular supply. So we do have one coin, but we have account-based models on each individual chain. So that if I, on one chain, wanted to pay myself on another chain, I would have to actually submit an atomic swap type. We do it by SPV, and that comes later in the deck, but each chain maintains its own ledger, essentially. Yes.
Still do all this stuff, but each chain have its own unique genesis block, or do they have a...
So there's one giant genesis that contains all of the genesis blocks.
Oh, okay.
So
Yes.
essentially any new chain would be a hard fork. Doesn't mean you throw away everything, but essentially everyone has to. If you change the structure, yeah.
And we haven't decided yet whether we're going to spawn new chains out of nothing or whether we're going to say that chain 1 just splits into 5 chains, and so that they'll have their history of their own. Everybody's history belongs to chain 1 if you spawn from it. We're working on it.
And is it basically your bottom, top, working backwards? Sorry.
This graph structure is just for discussion purposes. We'll keep moving forward into graph structures that become more realistic.
But this process, if you mean those are fixed. So right. You always have the previous.
In fact, let's just do this. Let's just do this. This is the 20 chain potential configuration graph. So all of these graphs that we've been looking at are solutions to the degree diameter problem, which is how do you have the biggest possible graph that has the smallest fixed degree and diameter. So degree is the number of other chains you talk to. In this case, the degree is 3. So 1 talks to 15 and 2 and 6. But in this graph, no 2 chains are any more than 2 hops away. The diameter is 2. So you never have to go any more than 2 blocks before everybody has all of the information for the network. In this case, 1 to 7. 1 to 6, yeah, so anyway, yes. So these references that before just looked like, chain 1 and chain 2 keep talking to each other, become much more interesting when the graph starts to become more complicated. In this case, the information from block 0, as more blocks are added to the network, the information from this black block is propagated to the entire network by the time you make it to block height 3.
Question?
Yes?
Correct me if I'm wrong, but is the reason why you're doing this to help with proof of work, or what was the motivation?
So we originally started out by saying, if we could just have side chains, but then make the side chain real, that would be great, because then you could just have twice as many transactions. So what if we just had 2 chains, but then we're like, but they're not really part of the same network, because you can't move money from chain 1 to chain 2, so they're really just different projects now. What if you could move money from chain 1 to chain 2, and then you could swap back and forth? Then you could do twice as many transactions as one chain, and then also have fungibility. So now, well, why stop at 2? Why not 20? Why not 10,000? You can pump as many transactions through it as you can make chains, as long as you can efficiently propagate the information throughout the network. Yes?
How do you enforce invariance on the global chain structure, such as each of these chains will only have degree 3, or you're only 2 hops away from any other chain?
That's just part of the hard fork configuration of how everything glues together.
So if you wanted to tweak these parameters, how hard would it be to do?
We'd have to hard fork the network to do it, which we have plans to do as we grow and as the network becomes congested and suddenly 5,000 transactions a second isn't enough anymore. Then we can go to a bigger.
Choosing those graphs is pretty straightforward. Well, it's a hard problem. The optimal graphs are not known as you get bigger, but the graphs close to optimal are known. So it's relatively an optimization problem. It's not that it's a very complex thing. In choosing.
Fortunately, smarter people than us have applied their brains to the degree diameter problem for a pretty long time, and they know the right configurations.
Random regular graphs are a great choice. They get very close.
All right, graph theory. All right.
No, it's not a hard problem. It's very clear. You want a low degree and a low diameter.
Yeah.
Whatever happens.
Yes.
If you split up a blockchain like this, then each individual chain away has a fraction of the hashing power on it.
Truth. Yes.
Also lowered the cost of doing a double spend attack on an
Aha! Oh, this is great. I should have prepped you for these questions, but I didn't, and you're asking them anyway. This is great. We're immediately going to go into that. Yes, this is great. Okay. So, the question is, if it's easier to hash a new block, that means that, Joe, duplicitous double spender, could replicate chunks of the network, and then he could pay you Bitcoin and take your car, and then sneakily behind your back go and erase that transaction where he paid you Bitcoin. We will talk about that. But the idea is that all of these references in here, these are the same way that uncle blocks in Ethereum give it power. Having uncle blocks means that there are more references that a duplicitous spender would have to replicate. There are more blocks that they would have to fake in order to erase the history of the Bitcoin transaction where they bought your car. So not only, instead of just having, if they wanted to replace this block in Bitcoin, they'd have to replace 1, 2, 3 blocks. In Chainweb, they have to replace not only this block and this block and this block, but also all of these other blocks that contain any memory at all that this black block ever happened. So that's the reason why they're all linked together like this. Not only so you can swap money from chain to chain, it started as we would really like to have throughput, but the security property is what really gives us the cool speed features. So the solution to a block is referenced by its peers. Each peer is referenced in the subsequent one. This reference tree becomes exponentially large very quickly as you progress until you're propagating the entire network. Within diameter number of blocks, an attacker would have to replicate the entire web in order to replace any given block. So, yes, this is terrible graphic on this projector, but that's what's on the t-shirt is the Merkle cone. It's a 3-dimensional Merkle tree. So this is the reference for this particular block. Right, go back. So because you only have to wait diameter number of transactions before a block is propagated to the whole network. It means that you only have to wait diameter number of blocks before you're confirmed. Unlike, have to wait 6 blocks or 8 blocks until you've decided that you're not double spendable. Here, you only have to wait 1, 2, 3 blocks. And suddenly you're pretty confident that you're not double spending anymore by like a ridiculously small number if you go check out our proof paper. Yeah. So that's where the security and the speed both come from. Right, so because we're a proof of work network, we need miners. We talked about this a little bit earlier, but the idea is that every miner will mine all of the chains. There's a little bit of crypto anarchists don't like this because they like the argument that any miner should be able to have a GPU in their closet that can produce a fully functioning node. If you wanted to, you could listen to the header stream and only mine one chain. In that case, you could have, something in your closet that you could use to mine. But the reality these days is that miners have formed large consortiums, so we might as well take advantage of it in terms of having them keep the network as synchronized as possible. So it's just, they exist, it's going to happen, we should just accept it. Right, so the coin is, to people to incentivize miners to put their transactions into blocks. We are a fixed supply, but the horizon is 120 years. So in 120 years, if we're still around to deal with the fact that there are no new coins being mined, please, may we have this problem. Separate wallets exist on each chain. We're using an account-based model. And if you want to pay somebody who's on another chain and doesn't have a wallet on your chain, you do it with SPV. Cross-chain currency transfer. Okay, so here you are deleting coins on one chain and then recreating them on another. We went through a brief phase where we talked about calling this the Lazarus protocol. But then when we start talking about things like making crypto kitties on the platform, then you have to start talking about, well, if I want to move my crypto kitty from one chain to another one, I have to murder my crypto kitty and then resurrect it on this one. And it just starts getting weird. So we don't know. We're just going to call it SPV for now. Yeah, so
teleportation.
Pardon?
Scotty, teleport me.
Yeah, maybe teleportation, but specifically the way that works is you delete them, which generates a receipt in the smart contract layer, and then you wait for that proof to propagate out through the network. Diameter number of blocks for confirmation, and you're going to wait diameter number of blocks before you do anything anyway, so it doesn't really matter whether you're doing it on the single chain transfer or cross chain transfer. When the proof is fully propagated, you can check it on whatever chain you're on, and then you can redeem the receipt, which consumes the transaction ID from the delete, and you have moved your money from chain to chain. Oh, this is our little diagram. Oh, yes?
And the deletion from one chain is the creation of another, but basically it's common, right?
Right, well, it's also asynchronous, which is great.
Yeah. You don't want to delete it and then not recreate it and then that money doesn't.
Well, it doesn't matter because it's the onus is on you as the recipient of the money to redeem your money. If you decide never to redeem that money, that's your problem.
But then the network's lost. Is that okay?
Who cares? So in theory, if you wanted to, you could create your smart contract to have a timeout on it. So that if the coins aren't redeemed within a certain amount of time, then it reverts the entire operation. But the onus is on you on that one as the developer, whether you want to have permanent burn or not.
So the damage to yourself is strictly more than the damage to the network that you do by destroying money. It converges towards being the same if you own all of the money. At that point, the next.
Exactly. That's it.
Right, I'm just saying, yeah. The economic incentives not to destroy money are pretty good.
Unless you just hate the world.
I mean, all right.
You destroy your money.
Fine. All right, so time goes this way in this chart. References point backward in time. So block height 0, I delete some coins, which makes a receipt. You wait for the proof to propagate over here, at which point you can redeem them. So, yes. So it takes the same amount of time. Diameter, you're going to wait for confirmation time anyway, so it doesn't really matter whether you're doing an SPV or whether you're doing a payment on chain. You don't have to redeem at the same time you delete. And this works also for balancing smart contracts. So if I have an application that's currently running on one chain and I decide that I want more bandwidth, then I can just move it to another chain, and I can double the number of chains that my project is working on.
So this deletion, recreation is sort of a form of cold storage.
Could be.
Delete it, print out the receipt, put it in a safe deposit box, and 10 years later, bring it back.
Sure.
Another question. It seems
Yes.
like a lot of work to avoid something like using proof of stake or something.
Yeah, but proof of stake hasn't actually proved to me that it will actually work.
Let's say it did.
Great. Oh, all right. What else are we assuming?
What's the advantage of this? And I'm kind of asking a rhetorical question because Will told me.
Is he testing me remotely?
Right.
Okay. So, I mean, philosophically, I believe in proof of work because it is this amazingly simple, informationless way for people to participate in the network. It literally requires no information at all as to whether somebody is a rational actor or cares about the project or has money involved or has millions of dollars or has no money at all. If you've shown that you do the work, then you are valid. And that there is a beauty to that, that if we can figure out how to make that work in a context that will actually provide value, then we don't need to go through this like, well, you know, you staked, but then you withdrew your stake and therefore you can long range attack, or, you know, you staked, but it wasn't enough. And so, or you voted for this thing and we need to slash you because we think that you're a bad actor. Like all of that game theory stuff is contingent on whether humans are doing the things that we expect them to do. This is just math. It just works.
And isn't it nice that you're being rewarded for doing work and not for already getting rich?
Yeah, well, that's actually kind of what the point that he made, which I thought of, and this comes from his time at SEC, was that the proof of stake, you're actually an individual with the most stake, or an entity is making a decision, and that becomes like a liability.
Well, there's also like money transmitter problems with
Exactly.
laws.
Whereas
But
this is just a machine, and so there it doesn't have that problem.
yes. So recap, we talked about scalability because we have many chains in a graph structure. Security because you have all these references that are sort of like uncle blocks, but they're not useless, they're actually useful. And speed because we have this security feature, we have a low confirmation time. Also, we're hiring people. If you are interested in working in Haskell full-time on a really cool thing, we have a language design team. We are going to build a very large-scale production Haskell system. And also, we're going to need people that are interested in writing Pact to help us go out and spread Pact to the world. So, yes.
Have you considered alternate proof of resources like proof of storage?
I like Chia's project a lot, Proof of Space and Time. I think they're super cool. Bram Cohen is brilliant. That's just not what we're using.
Okay.
I want to see their project work too. I think it's cool.
It's also using as much energy as layer limit to fund Ethereum for transactions.
Yeah.
How much does the financial system
Right. Our traditional rebuttal to that is like, how much money do we spend maintaining Swift or like ACH? If we could just get rid of that and use this instead, I think we'd be better off. Yeah. So, yeah. That's it. I'll take more questions. All the questions. Or we can go have a drink.